All right, let's kick things off. Welcome to the seventh installment of the Local First Meetup. It's been fascinating and inspiring to see everybody's work in these meetups over the last few months. Also, we have crossed the 1,000 member marker. I know we shouldn't laud vanity metrics, but it also speaks to the passion there is for user owned data, offline enabled, and local first ecosystems. I'm really thrilled to have the people speaking today. And first off, we will have Mikhail presenting from AnyType. And I don't know if you guys have followed the news or the posts. They just closed the round. It's an exciting time for them, but they've been at this for a long time. And Mikhail specifically has been working on the sync technology that makes normal Web2 products look like Lego games. Why don't you take it away, Mikhail?
Okay, so let Gianna start then, because she was. It would be better that she tells the general info, and then I can get a little bit of detailed stuff.
Great to have you here, Jana. And for those that don't know, she's the CEO and co-founder of AnyType, and she's really passionate about digital activism. I've been following her for years now, and it's exciting to have her give us a talk. If you can go off video.
The share screen button is blocked. Awesome. Okay. Hello, everyone. And before Misha starts to tell more about anything, I would like just to give a short introduction on why actually we are building AnyType and anything, and it will answer the questions why this kind of design decisions are in the protocol. So I hope you see my screen, and it's inside AnyType. And I would like to say that the main objective for us is that we at AnyType believe in fundamental digital freedoms. We believe that things like the privacy of thoughts, the freedom to connect with those we trust, and the freedom to create and manage the communities of our choice and governing things that we create digitally represent essential digital freedoms that we believe are as important to the world of bits as fundamental human rights are important to the world of atoms. And by the world of atoms, we mean our normal reality, and fundamental human rights represent the foundation on which, and the governance surrounding them represent the foundation on which any well-governed society of today is functioning. I think above, so we don't have a consensus on fundamental human rights. It's put above the consensus, and the states and the governance around these human rights are this biggest innovation that we had for the world of atoms. And I think that fundamental digital freedoms have the same meaning for the world of bits that represent the same kind of innovation for this for it. However, the world of bits today, unfortunately, does not respect these digital freedoms, and that's because application developers are being keepers of keys. So they currently in Web2, application developers control the keys to the accounts of users, and because they control the keys, they can determine who can access the account, who cannot, which information is shared and distributed, which posts are promoted. All of these points of control, and because they control this, they control our freedoms. And this means that some corporations with their management and shareholders become governing these freedoms, and we believe corporations are just ill-suited to govern such matters. And that's why this was the whole idea behind designing AnySync, that AnySync should support digital freedoms. And that is why the decisions that we made that make like why AnySync is the way it is, because we thought these are the things that it should provide. First of all, of course, user-owned keys. Secondly, local first peer-to-peer and end-to-end encrypted to make users less dependent on the software provider. both that they don't depend on the backbone all the time, that they can sync without having the need for a server, and that their whole information is encrypted so that we have this privacy of thought and other freedoms realized. And an important concept here that we talk usually is autonomy from software providers. So we're trying to design in a such a way that the users of this protocol are fully autonomous from the software provider, so from us or from anyone else. And that's supported by the open data standard, full data portability, and also an ability to self-host. So any type has full self-hosting capabilities. Of course, for this, we need to make the code open so that anyone should be able to verify it's working. And a special challenge for the recent protocol was to make it high performant. And Misha will talk a little bit about it. So on top of AnySync, we built AnyType because, of course, we think people use products, not protocols. And you can think of AnyType as a graph-based space builder, and spaces are just analogs of websites that are graph-based, and which means that they speak the same language of objects, types, and relations, so that all spaces are having this interoperable standard. And if you have some tasks in one space and some tasks in the other space, you can aggregate across spaces. It just makes spaces speak the same language without APIs, without some the need for developer skills. And final thing that spaces are built without code, so you can with just a drag and drop editor build something like that I use as my working space, or you can build some personal space with maybe some meal planning or with some other stuff. And currently Anytype is launched with private spaces, but we're currently developing shared spaces for teams and communities, and public spaces for personal profiles and other things. We are building it with our mini association, which is an open community for builders. That's it. That's a short introduction for missing.
Wonderful. Thank you, Jana. Off to you, Mikhail.
Okay, one sec. Okay, do you see my screen now, or it's still yes? Okay, so basically right now we are, the core of this is like a collaborative editor, right? So, and we have this use case, like one person creates a note at home, then the other guy, and because it's offline first, we need to sync changes across devices without, it's offline first and peer-to-peer, we have to sync changes across devices without having, you know, like a central server and this kind of stuff. So just as an example, we see that we have like three guys. Let's say we have Bob, we have Jane, and we have Alice, and they create Bob starts the document, and Alice and Jane, they edit the document in different places. And then when all of them go online, they need to have the same state of the document, right? And so therefore, we need an algorithm which works with branches and merges them automatically. So basically, we need a CRDT algorithm. And before we go into that, we need to say that like we have two layers, right? So first, let's say is like underlying layer is the infrastructure layer, is how the state is you know, synced across the documents. And then we have like more, let's say the app layer, where we have the state, which is represented as a tree of blocks. So you see we have a block-based editor, and we have basically the state represented as these kind of tree of blocks. So, and when user makes changes, he or she updates one or many blocks. And so we, for example, that's how it looks like. So for example, Bob created the root block and Jane added one children, and for example, Alice added another children. So before we go into this algorithm, we just want to quickly say that anything, so this main like infrastructure layer contains of different parts. Let's say on the bottom part, we have objects and files, then we have spaces, and then we have networks. So if we, so basically the first part is our CRDT data structure called CRDT graph, which is a direct acyclic graph. And the idea is that we want to maintain eventual consistency between states of different devices or different users. And the idea is that it is a graph-based structure based, which is content addressable, right? And so, for example, let's say Bob made 3 changes, then Alice created another 3 changes on top of Bob's changes, and Jane in parallel, so that's the same story, created like 2 changes on top of Bob's changes. So the idea is that when they both go online, we want them all to have the same structure, right? And it's basically will automatically build in that way because each change contains it's content addressable, so each ID is basically the hash of the content, and the other part is that it contains reference to the previous IDs. So when we are talking about the document, it's basically represented by first some kind of head or heads, right? And the root of the document, right? And going from head to the bottom, you can basically build the whole document, right? And we can say that each new change which we create on device, it tries to merge all the previous changes, all the previous heads, basically. So the other idea which we have is then at some point in time we make things called snapshots. That way we don't have to traverse the whole graph, but we can do just before before the common snapshot. So and after we build this graph, we need to iterate across those changes. And how we do this, we just use a topological sort, starting with the root and then going up. And we start, so when we have branches, we decide to the branch with the lowest hash. So here we will go through alias A, B, C, then so from snapshot 2, then A, B, C, then D, E, and then F, because F is based on these 2. So this is just basically a topological sort, nothing that much interesting. And and what happens when, for example, imagine that there were like 3 guys, and then we have another guy, John, who actually based his change off the first snapshot. Then we actually first start by finding the common snapshot of those guys and then rebuild the whole graph altogether. So that is like very quick description of how this works. And so in the summary, we have like simple, fast CRDT data structure. The data sync does not grow linearly in size because we use snapshots, right? So the ordering captures the way how the messages were built. So if A was made, let's say, if B was made later than A and it was based on A, then this will order will, preserve. And it's secure and verifiable. So let's quickly talk about files. We use IPLD, but not, so let's say we can divide IPFS in 2 parts. So first how to store data, then how to find data. And because like we know where our file nodes are, we don't use the bit swap mechanism because it's takes a lot of time, and we still use the IPOD data structure, which is essentially a Merkle DAG. You can see a lot of info on the internet about it. So, and this works pretty fast, right? because again, like for us, it's very easy to find the nodes where the files are placed. So a couple of words about sync protocol. So we have like two methods basically, which is head update, which we broadcast as soon as the document changes to all our peers in the network and all the nodes, right? And the nodes also are peers, so the sync protocol is like symmetric. And so basically each time, yeah, we update the document, we broadcast new heads. And when also we receive some updates from other persons, we also send new head updates that we changed the document. So this how it looks like. Imagine that we have like C and B as head updates, and this is like the good case where it's exactly we can apply it to the previous state and it works. And the worst case scenario that we can't apply them right away because, for example, something is missing, then we have this full sync request reply mechanism where we actually resend the missing part and kind of diffing the states of the document. So here we will, after in response, we will get all the missing parts and the documents will be synced. So in the gist, we still find common snapshots for different versions and then take heads of version 1 and version 2 and determine the difference. So let's quickly talk about spaces. So imagine like spaces is like, let's say, just different union of objects. And for example, Bob and Alice, they like fishes, so they joined the space of fishes, and Alice and Jane, they like cats, so they joined the space of cats. So and this is like how you can visualize what space is. And underlying structure is like space. It has an access control list, and it contains objects which are the CRDT graph data structure. And the objects, they refer to the current head of access control list. So so with access control list, we need a consensus because it's a list and not a CRDT data structure, and I will tell you why really quickly. So how this looks like if we try to combine the objects and the ACL. So each new change referred to the current head of ACL, and it is also encrypted with the current symmetric key in ACL. I will not go into deeper detail why this works, but because we don't have that much time. So in terms of encryption, we have this thing that the space has like current symmetric key, and the symmetric keys of objects, they are derived on the basis using derivation paths and the IDs of the document, right? So it's so each object has its separate key, and to transfer them to users, we encrypt them with like public keys of members. And for example, when we remove the user, we create a new symmetric key, and which encrypts the previous one, but we don't provide, of course, this to removed users. So removed users can only read the old contents of the space by design. And so when the new user is added, he is needed to get only the last symmetric key, because then it's kind of this chain encryption of those keys. So why we use lists? It's like really simple, because imagine if we try to use the same CRDT graph data structure, we could have conflicts. For example, imagine there is record 1 and record 2.1. So there were 3 users. In one case, we removed 1 user, and in the other case, we removed the other user. So we have like conflicts in symmetric keys, and maybe in the we also added the new user based on the left branch. But when we try to build the state, we essentially see that we go 1, 2, and here there will be conflicts. So basically, we'll apply only one removal of one user. So it makes kind of inconsistent logic of removing the users, because you will never know if your remove succeeded in the end or not. So that's why we decided to go just with like lists. And we have this kind of compromise where offline you can add new documents to space and change existing documents, and online you can change the access control lists. So scaling, because we don't want to have all spaces on one node. We want to somehow distribute the load in our system. We have like this kind of algorithm where we use space as hash to determine the partition, and then it's just modular hashing, and then use consistent hashing to take the closest nodes to a partition hash. So for example, and then we try to balance it. That's, sorry for the picture, it was the easiest way I could do this. So we have space, for example, we take the hash of space and we just get the partition to which the space goes. So this is just modular hashing. And then we just, for each of the hash, we just use consistent hashing for each of the partitions hash. And here we say that for space 1, we take partition 1, and partition 1 we will take node 1 and node 2. So because they're closest, the same with hash 2 will take node 1 and node 3. And here, and in this consistent hashing, we just duplicate these nodes many times, so it would kind of be, more or less balanced. And then in the last case, we don't take the closest node, because we also want to balance it a little bit. So it's something like this, and it gives us pretty good results when we have a lot of nodes. So when we add, for example, new node, for example, from 68 to 69, we have only 2% of partitions which are moved around the cluster, which is not that much, which is, I guess, fairly okay. So this is, and the other thing which we have is kind of resharding. So when we have like one configuration and we add another node, we see that partition 2 changed the node, and we have to do resharding for that configuration. The algorithm for this we are writing right now. And so the networks, the last part, basically it's just a lot of different stuff, but the idea is that users, they can communicate between themselves peer-to-peer, but right now only in local network. And they are members of space, and the space is managed by a group of nodes, and different space is managed by different groups. And users communicate also with different nodes, so the load will be somehow balanced. And to create the space, you first have to go through coordinator, which is the node that does a lot of different stuff, but mainly serves as a gateway. And the consensus nodes, they manage access control list, and the file nodes, they manage files. So that's the gist. And also, so how do they know about each other? They take the nodes configuration from coordinator, and so also the users get the same configuration from coordinator. So this is how the configuration looks like. It's just like the network IDs with different nodes and stuff, if you're interested. So, and the recap, so we talked about scaling, network scaling, sync, spaces, files, objects, ACLs, and CRDT graph. Thanks a lot. I tried to make this as fast as possible. Thanks.
Thank you, Mikhail. That was light speed, but also very informative. Next up, we have, I believe, will be talking to us about triplet. Why don't you take it away?
All right, everyone can hear me? Let me just get my slides up. We got slides. Okay, cool. Thanks, Jans. Always impressed by these talks, so quite an honor to be on the stage. So today, I'm going to be talking to you about why I think we all need a full stack database, application developers, and how us at Triplet are trying to fulfill this vision. Also, while I'm presenting, there's a couple of Triplet developers in the audience as well, so feel free to drop any questions in chat and they'll answer them probably quicker than I can. Okay, so first off, just a little bit about me, some background. Most recently, I was a software engineer at Google working on the search core ranking team where we launched new features that showed up on the Google search page. And after that, I founded Aspen Cloud, which was part of the Winter 21 batch and at NYC. And I'm also a resident of Nashville. So if you're coming down to dance at a honky tonk, let me know and we can talk about local first software. So the important part is at Aspen, we pivoted quite a bit and we built a lot of different things, but most recently, and like the most influential product to what influenced Triplet is this app we built called Aspen Spaces, which was designed to be the WeChat of the Western world. And unfortunately, not a lot of people actually wanted to continue using it. So we're no longer maintaining it. But the important part is it was a local first chat app that had tons of little games and mini apps you could use with groups of friends. And so we had to solve a ton of local first problems. And we realized that we were spending like over 50% of our engineering time just working on like sync and kind of like data persistence and data consistency. So ultimately, we decided to build Triplet and focus exclusively on that and help other developers build these types of apps. So let's quickly talk just about stacks. A very simple, like intentionally overly simplified view of the world is you have thin clients and thick clients. So thin clients are just like, either just like a pure API, they're server driven, they're maintained and built by backend developers, like MapQuest, one that is like very old, a lot of old apps that are just like, basic static HTML. And like maybe Netflix, I guess would be another good example. Then you have thick clients, which are like, traditional desktop apps that have either a very simple server or no server at all. So like Microsoft Word and Photoshop are great examples of that, where for the longest time, they didn't have any kind of sync capabilities, then slowly added like, file sync and stuff like that. But as we all know, modern apps blur these lines quite a bit. So most of these logos you see on here are apps that are, for sure, like rich API'd, like server driven applications, but they also have very capable clients, like very thick clients. There are thick clients and thick backends. And so like, Spotify, famously a music streaming service, their big innovation was making it so that streaming music felt as like low latency and responsive as like listening to music on your iPod. And same thing with like Gmail and Messenger and Google Docs. They blend this experience of rich cloud-based applications with very functional standalone apps, like client-side apps. So when this kind of new era of apps came along, we as an industry also defined a new term for the folks that build these apps. And we call them full stack developers, right? I think many of us would identify as being full stack developers, someone concerned with the end-to-end experience, literally from database to CSS if you're building on the web. And along came a bunch of full stack frameworks. I'm sure a lot of you have at least tried one of these. Next.js is hugely popular and one of the most loved frameworks on the Triplet team. And they kind of like changed the paradigm a little bit. They allowed us to like write a component that could seamlessly run on the server, be rendered to HTML, and then run on the client. Also, without having to have to write it twice or really think about it. And of course, there's as these frameworks have matured, you can decide the behavior on the server and the client a little bit differently. But you got to deploy and maintain all of your server side and client code together. And this is like hugely productive. And I think it's like a stepwise kind of like step forward and like create React app has almost been completely replaced by Next.js, and I think many of us won't be going backwards to building just a server side or just a client side app when we're building, a full experience for our users. But there's this unfortunate reality that we can't get around. And so even though we deploy our server and client together now, there is a very tangible distance. And even if you do the fancy route and deploy to an edge server, there's latency that you just can't mitigate, right? We can't move faster than the speed of light. And frankly, for highly interactive apps, waiting for the server is too slow. Even at like 40 and 50 milliseconds, which would be like you're doing your job really well and your server's well optimized for responding, your users will notice that latency. And not only that, that latency really adds up. So like, for example, what I mentioned, MapQuest, which is essentially defunct, got completely replaced by Google Maps because Google Maps solved this problem where you got the time to do 120 actions at 150 milliseconds latency, like maybe you're loading tiles in a map view, it's going to take you 18 seconds versus if you're doing it like locally, it's going to be under a second. And so that's like why Google Maps basically was able to completely replace MapQuest, because they brought the best of both. So that's why we think that database needs to go full stack. And this is like an idea I think many of us in this group are fully aware of. And partially, we're just trying to add this term to it, how to describe this end-to-end experience. And so, taking influence from these full stack web frameworks, what would a full stack database look like? Well, you would for sure only have to write your query one time. And that same query, unmodified, should be able to run on the server and return results, but also be resolved from the cache. I don't want to have to write two different queries, God forbid, in two different languages. I just want to write it once. I also want that query to be reactive and automatically subscribe to data changing on both the server and or the client. Again, not having to write two different handlers or two different subscribers. And with that, I also want this cache that I'm kind of referring to be automatically populated. As many of us know, working in the SQL space, is that a SQL table and SQL rows don't perfectly map one-to-one to JSON. So I don't want to have to think about how things get normalized and stored on the cache. It should be all automatic. And of course, with these full stack frameworks, we've got a full stack language, which is TypeScript. I want good integration of TypeScript, and I want type hinting in my IDE. So when we look to the current ecosystem, I'm wondering, does anything solve this very well? And I think the closest thing is probably Firebase and Firestore. And if you're unfamiliar, Firestore is like a real-time serverless database. But it falls short in a couple of different ways. One, it's not open source. It's completely controlled by Google. It has pretty limited querying capabilities. It's completely schemaless. So if you want, good TypeScript integration, you're just going to kind of do loose type hinting that you kind of have to manually write and keep in sync. And it's also not necessarily going to be true. It can also get pretty expensive. There's some horror stories there, but most importantly, it's you only have one vendor to choose from. So if prices go up, your only option is to pay the piper or move to a completely different database. So now I'll kind of share how Triplet makes some of this work. This is kind of going to be a very high level overview, and there's a lot of details, but feel free to, again, ask any questions in the chat, and one of the Triplet developers will hopefully answer you quicker. So as you can probably imagine, Triplet runs on both the client and the server. But most importantly, it's not just there's a Triplet database on the server and then there's a sync engine on the client. It's the full query engine ships on both, so that any query that you could make on the server is fully capable of being fulfilled on the client. We use WebSockets to transfer data in between the client and server. And also, it's worth noting that what we're talking about here when I mention a cache, it is like partial replication. So this isn't like sync the whole world, which we think is kind of table stakes for web apps, and like waiting if you're using like Figma or Notion and have to sync your entire database is just going to make sharing really difficult, especially when you move across devices or share with new people. The other part is with like a partial cache, we also want incremental updates, and not like a lot of like existing databases will have reactive queries where you will like pull the database, or even if it supports like kind of native reactivity, it'll refresh the entire query. You'll get that whole view. But this is just like with a syncing system, this just doesn't scale, and you'll end up like really crippling your database even with a small number of users. So we really want minimal deltas going between our clients and our server. And then another key piece of this is schemas, and a lot of like the metadata around like validation, authorization, etc., can run first on the client. So that's also maintained between client and server. So you'll get really instant feedback, even if you're offline, that like, hey, this doesn't match the schema, or you're not authorized to do this, rather than having to wait, sometime like you get off your flight to then find out that, that note you added doesn't fit and needs to get deleted. And so to zoom in a little bit on the client, we actually have two different databases running side by side on the client, and Triplet kind of abstracts that away. So you have a seamless view over both the outbox and the cache. So as you're querying, it doesn't matter like where the data is, you just get one response. The system is really nice because the client can just write to the outbox, and that gets synced and sent to the server, and then the server exclusively writes to the cache. And what's kind of nice about this is you can also configure durability independently. So your cache maybe could be in memory, and it's like only persists with the session, and the outbox is strongly durable and persists to IndexedDB. Or you could have them both persisted for a really like robust offline experience. And the other nice part about having the outbox completely separated is when you do need to roll back, for example, if some change isn't authorized by the server, it's just a matter of deleting it from the outbox. You don't have to do like write the inverse or the reverse of any transaction and try to like keep track of the types of mutations you made. It's simply just removing data, and then the next query runs and you get a refreshed view of the world. So this actually, the other key piece of this is, by having the outbox and cache be these explicit databases, it's very easy to tell the sync status of a given mutation. So if it's in the outbox, you can essentially know that it is pending and hasn't been synced yet. But as soon as the server acknowledges it, our client will move it from the outbox into the cache in a single transaction. So that's a really easy way to get like free syncing statuses. So for example, an example near and dear to our heart, building Aspen Spaces, the chat app, was being able to have a very reliable and simple way to deal with the kind of sent status. So like in every chat app at the bottom, there will be like what we call a staging area of where messages that are pending will live, and then all the messages that are committed will be on top. And in Triplet, it's super simple. You just have two different queries, and one is the confirmed messages, which are things that live in the cache, and the pending messages, which are things that are still in the outbox. And because Triplet is like transactional, you'll never see any like weird states where a pending message or a message exists both in the pending state and the confirmed state. So your UI can just like simply subscribe to these two queries, and it'll efficiently and reliably move them between them. And so the kind of undeniable other component of this is, as we all know, anytime there's like client and servers and syncing, it is an eventually correct system, or like it's a distributed system that needs to be eventually correct. And there's no way to get around that, right? Unless you do round trip to the server every interaction, which we've ruled out. So let's look at just a quick example here. So this is what, typical JSON document, we've all probably worked with something like this. Looks like for like a chat message. You can kind of see here, this is like a message envelope, but also it has a reaction from another recipient. But as we know, like what we don't want is to have like mutually exclusive edits where if I like edit the text of this message or two people react, you want to get all of those edits. You don't want to just get like one reaction and not the other for concurrent edits. And you really just don't want conflicts either. It's very awkward, especially when we know these changes can be interleaved. And so, no surprise here, CRDT is to the rescue. So the way that we do it is super, super simple. We use Lamport timestamps, which just, for those who don't know, is just a form of a logical timestamp rather than a chronological one. And the way it works is each Lamport timestamp will have a monotonically increasing integer that every transaction you increment. And when you get new information from the server, you also increment there. And then your client ID. And this helps with like collisions, so that if two people update the same property with identical, integers, like the timestamp, that you can then just kind of arbitrarily choose one winner based on their client ID. And that will, and most importantly, that will be consistent across all the clients. So eventually everyone will converge. So we add a Lamport timestamp and update it on each transaction, and we add it to every properties, so you can see that like the original message has the timestamp 1 client 1, and the emoji reaction has Lamport timestamp 2 client 2. So to actually store this, we put it in one simple table, and it's kind of flattened out. So you can see these nested properties become essentially kind of like compound attributes. We actually like store these as an array inside TupleDB. If you haven't checked out that library, it's really cool. It's like modeled after Foundation DB, so definitely take a look. And also, if you've ever played with Datomic or any like data log engine, this should look very familiar. It's the kind of classic entity attribute value triple store. And this is like really nice for us because it makes querying a lot easier rather than like dealing with like nested documents. We have one flat structure that we can index very simply. So we add an index that's like a composite index on entity attribute value, as well as attribute value entity. And so even like long-term, this will help with like aggregations, but this format itself lends itself really well to relational querying, and a lot of graph databases model their data this way. So on the subject of relational queries, in our original version we had that was like schemaless. We had relational queries and we've recently rolled them back, but this is kind of like our upcoming roadmap. We're going to be adding reorderable lists. We'll probably use like fractional indices there. We've tried a bunch of like lexicographically sorted sequences, but that it like doesn't work that well. We're going to be adding presence, and of course, like a really like fun one we're excited about is incremental aggregations, so that you could potentially even like alongside your database be running like kind of like analytics very efficiently, because you're just getting incremental updates to your data, and then you're processing that on the client. Also, right before this, we switched our wait list from a classic like form on our website to be totally encapsulated in Discord. So we need help testing this out. So come join us in our Discord and do the command /waitlist and see if the bot responds to you, and help us debug it if not. That is it. Thanks, folks.
Wonderful presentation, Matt. And again, triplet.dev if you haven't hit that up yet. Next up, we have Anselm, and I shouldn't even give him introductions because he's given talks in Berlin with the Berlin Local First Meetup, and I also got to check out Jazz Tools from a couple of YouTube channel links and stuff like that. So if you haven't run into him, Anselm's been tackling Local First for a while. Really looking forward to hearing what you have for us.
Thank you very much, Jonathan. Share my screen. Okay. So yeah, thank you again, Jonathan. My name is Anselm. My main idea is that I think it's way too hard to build software, and that's why I founded my company, Garden Computing. And I kind of made it my mission to find good abstractions that make it easier to build software. And roughly 3 years ago, I learned about CRDTs and started thinking about local first as a new way to build apps. And the main thing I realized in my experiments is that CRDTs are really just one piece of the local first puzzle. Like, you definitely also need infrastructure to sync and persist changes, and you really also need to solve identity, security, and permissions in a local first way as well. And as more people are getting interested in local first, we're starting to see libraries and frameworks for each of these areas. But I think having to integrate them once again creates too much complexity for each app developer. And ideally, we want to include all the ingredients of local first in one abstraction that takes care of all of these needs for you. And that's really what I'm trying to do with Jazz. I'm calling it a framework for building apps with secure telepathic data. That really encapsulates what I think is needed. Telepathic here means that all data instantly syncs and persists wherever you want it, while you just interact with it as if it was simple local state. That's all that you should care about, and that's mostly what CRDTs and sync give us. And the secure part of secure telepathic data means that identity and permissions are also taken care of in a way that suits local first. And for this purpose, I developed a very dynamic form of good old public key cryptography and wrapped it in a high-level API of counts and groups, which you can create anywhere, including on the client, since they themselves are based on CRDTs as well. And in groups, you can set and dynamically change members' roles, such as reader, writer, or admin, and then these determine the permissions on objects that are owned by that group. It's really as simple as that. And this abstraction lets you implement secure collaboration flows like you would expect it in any traditional Web 2.0 app, but completely local first and offline capable. And by design, the cryptographic permissions are enforced locally, so you also get end-to-end encryption and verifiable authorship for free. I really believe in open source, so Jazz is open source, but more importantly, I believe in open protocols. And again, I think each of these parts are not as valuable on their own as having one comprehensive standard for the integrated whole. So at the core of Jazz, there's a new standard for secure telepathic data, which I'm calling CoJSON. CoJSON includes 4 basic collaborative values, or co-values for short. These are exactly the CRDTs: maps, lists, streams, and just static objects. It defines how the cryptographic permissions work with identities, accounts, and groups. And it also defines how the syncing protocol looks. Jazz is then a convenient framework on top of that that lets you run CoJSON compatible nodes in a variety of environments, integrating well with the existing abstractions there. And as the first example of an environment to use CoJSON in, I just released the first versions of Jazz Browser and Jazz React for building web apps with Jazz. Jazz React in particular gives you a really nice reactive API on top of CoJSON. It just looks like a local React state, but magically syncs between participants and devices, and it persists data in your browser's local index DB as well. But to make building apps with Jazz React really simple, I'm now also running the first version of a service I'm calling Jazz Global Mesh. It's a CoJSON compatible serverless sync and storage infrastructure, which I'll offer as a cheap app-independent commodity. You can think of it as a CDN for sync and storage for CoJSON-based app. And using this as a service means that you can literally build a whole app just by building a front end and hosting it as a static site. It will have persistent state, both local and on the mesh, cross-device sync, user identities, and collaboration that actually just works. Let me show you a really simple collaborative to-do app that I built with Jazz React and Jazz Global Mesh. I'll tell you what's going on behind the scenes, and I'll show you what I think is the neatest thing about this example, that your app's code is basically just some CoJSON-based data models that you attach to some UI. So first for the app itself, this is what it looks like. First, we see this auth screen, which uses a special auth provider for JS React that uses the new passkey browser feature to authenticate me, in this case with Touch ID. So if I enter a display name here and sign up as a new account, it asks me if I want to save a passkey, I accept it with Touch ID. And then I'm logged into the app. So now I can create a new to-do list. Let's say one for groceries. And I can just add a couple items to it. And I will now simulate opening this on a second device by logging in a private tab and opening the same URL. So let me open that up over here. My passkey is synced across my Apple account, so I should be able to log in with existing account, confirm with Touch ID, and I should see exactly the same to-do list as on my other device. As you can see, everything is immediately synced between the two. And to achieve that, we had to write 0 additional code compared to the single device app. Now let's try to see what happens when the devices go offline and I continue editing the to-do list. I'm using a firewall op called Little Snitch to do this, and I'll just completely kill any connection to JS Global Mesh's sync server. And now if I go here and, for example, add something on the left and something on this device as well, and let's maybe take something here, take something here. You can see that these are not syncing because the connection is offline. But as soon as I take it online again, we should see these immediately syncing to the same state. Okay, let's try something more exciting. Let's try full collaborative multiplayer. I've never really tried this before with a group this large and as geographically distributed. So let's hope that this works. That the sync across like my mesh service all around the world works. As you can see, I have this little invite button here, and if I press it, it gives me an invite link. I first, let me see, I'll open that in a new tab if you want to join from a mobile device. And I'll paste the link in our Discord chat as well for you to join. And if you join that from your device, you should be able to just enter a display name and create a new account using the passkey feature. And after that, the same to-do list should load, as you can see on my screen. And since it's an invitation with write permissions, you can see that you can add and tick tasks as well. That seems to be working great. And yeah, to make this fully multiplayer capable, all I had to do was make sure that this to-do list is created within a group and make sure that the invite button is just hooked up to that group with the correct access rights or permissions. So you can continue playing around with that. That seems to be working reasonably well. See if I hit refresh, if I still see everything. Yep, there we go, perfect. Let's have a look at what the code for that looks like. It's a simple React app. On the top level, I have this one component I need to wrap my app in from JS React that's called with Jazz. I define the local auth provider here. That's what you saw with the Touch ID. And then in here, I have my app. In my top level component for the app, let's import a bunch of stuff from JS React. But the most interesting thing here is what I always start when building an app with JS. I just define my data model. And as you can see, tasks are pretty straightforward, but then the interesting thing is that I say that a task is a collaborative map of this shape. The to-do list itself is a bit more interesting. It has a title, and then this is slightly awkward because I haven't implemented the collaborative list yet. So we're just associating the individual tasks with the list by putting them as keys in here. And then again, a to-do list is just a collaborative map of this shape, right? And with that in place, we can start using that. So in our top level component, we use the use JS hook to get access to our local node with our locally persisted objects and where we are logged in as a specific account. Let's have a look maybe at the create list callback, where when we create a new list, we first create an empty group for it. And then within that group, we say we want to create a map object of this shape. And then we can use this edit callback to mutate it and set the initial properties. We just use the window location as a routing mechanism here. Next, let's have a look at what it looks like when we want to render our list. So this is maybe the most important bit of Jazz React, this hook called use telepathic state. All it takes is an ID of a collaborative object, and it gives us a reactive view onto that collaborative state, re-rendering our component whenever there are changes to the object, no matter whether we create them locally or they have come in from other devices or participants via sync. If we look at how this is rendered, basically if the list is loaded, we get its title, render that, and then render the table with tasks. Again, slightly awkward, we have to go through the keys, filter out the keys that look like they're an object ID themselves, and then for those we render a task row. Creating a task is really simple. Within the same group as the list, we create a new collaborative map with the shape of task content, set its initial values, edit the list, add the ID of the task to effectively add it to our list. That's all we have to do. Once that happens, use telepathic state re-renders our component with the new state. The individual task row is just as simple. We use telepathic state again on the ID of the individual task. And here, like, for example, the checkbox is so simple that I could just put the edit function directly in the event handler here. Maybe the last interesting thing you saw, I can invite people, and in each task row, we render this name badge account, and we can ask the task object, who was the last editor of the property text, and that gives us an account ID. And then inside name badge, we can use profile of this account ID, and it will, that's basically like use telepathic state for the profile of that user. In our case, the profile has a single property called name, but in your app, you could populate user profiles with additional information such as thumbnails or whatever makes sense in your case. If you're curious, I went through this quite quickly. Please check out the Jazz repository on GitHub, and you can have a look at the example yourself. Going back to the slides, I want to give you a quick glimpse of a final realization that I had and that led me to give this title to my talk, which is basically made me consider a much wider range of use cases for Jazz that I'm hoping to support soon. Because as you saw, having secure telepathic data is great for building greenfield, fully local first apps, but that is quite a departure from the traditional app architecture, as we can see here, where the backend and database are actually responsible for persistence, shared state, and authentication. But I realized that luckily the inherent properties of secure telepathic data mean that you can adapt it incrementally in an existing traditional app. I don't have too much time to go into detail here, but if you're interested, have a slower look at these slides later, and please ask me to tell you more details of how this will work. But the gist of it is that basically you create backend and front-end adapters for parts of your app to use secure telepathic data. It's quite low overhead, and you immediately get all the benefits that we saw in our fully local first app for the parts that you already converted. So offline support, cross-device sync, even multiplayer that works based on your existing auth. And all the data that you create local first is synced back into your existing database so that the older parts of the app can access it without any changes. The main benefit that I've seen in early tests of this model is that all your state handling all the way across your app becomes so much easier for the parts that are already converted to use telepathic data. And as you adopt it more, your app actually becomes slimmer and much more declarative the more you integrate telepathic data. I hope I'll have more examples of this to share soon, including ready-made adapters for common databases and all solutions. But in summary, I think that telepathic data is an incredibly interesting abstraction, especially if you take it to the extreme where, like here, where you completely get rid of the traditional database and the mesh also takes care of storage and hopefully soon queries. I really want to make Jazz a very versatile tool that anyone will be able to benefit from instead of it being like a strict framework that only works for some kinds of apps. So yeah, that's what I'm trying to build with Jazz. Thank you very much for your attention. If you're brave and you want to try building something with the early versions that I published a couple days ago, check out GitHub, follow Jazz Tools on Twitter, and definitely come hang out in the new Jazz Discord I set up, and I'm happy to help you with whatever you're trying. Thank you very much.
Wow, amazing presentation. And I'm also blown away by how much you've managed to cover in, 15 minutes. Everybody, I encourage you to check out Jazz. At this moment, and let's do a quick demo on any type if either of you are ready to show that off. And then we'll turn off the recording and go into Q&A for whoever wants to stick around.
Jana, will you do this?
Go for it.
Because so Jeanne is, I'm not sure if she's here. I'm not sure if I have like, let me check if I have like some cool example, but to be honest, I will just give you a super brief demo because I probably, okay, so Jana will do this. Jana, will you show like some beautiful accounts there?
So one of the coolest features is
Oops. Let me.
You're coming in great.
I can just share my I don't know how beautiful it is. 1 second. Sorry, it's so you wanted to see the demo of any type. So it's basically you see it's the way I structured my any type. It can be very different from how other people structure it. So I use a simple structure like that as my main dashboard here, and that's why I can here, for example. Also set up my sidebar, and in this sidebar here I use the widget for this is like tree-based widget where I, for example, can go inside different documents that we have. For example, we had some. Okay, maybe we have town halls. Yes. So you see, this is like your space here that you can set up with help of widgets, and I use this widget, favorites and recent, but I can use some remove some of them, for example, or add some new widgets, for example, with sets, and that's how I can build my sidebar. And then there are beautiful documents that I can use. For example, this is how we were presenting the space builder itself and the town hall that was some months ago, or I do my onboarding presentation here. Let me check. Where is it? And we also have something for many objects. For example, this is my idea set, just having some kind of ideas. And for example, whenever I can add a new idea very fast. For example, add a new idea. Okay, I don't have so I can have a new ID here and then go to a set of IDs. You see it's here, and then I can sort filter things, and all of this you can see is connected into a graph of my anytype. So you can see this is my graph. You see even I think somewhere here you can find Mikhail Rahmanov in my graph, because these are all my team members here. And that's basically also another set with all objects inside of my anytype, and you can have something like that. So this is my working space. I also have my personal space, but I need to change to relog in to show that with next in October we will release ability to have many spaces inside one account, and by the end of the year we hope to release access rights so that you will be I will be able not only have my personal space but have different spaces, and some of them share with my team members, or some with my family members, or some with my investors, or some with community. That's more or less I
The
can show.
graph is so powerful that it almost like shocks me sometimes. It wasn't very easy to see, but you can build any building blocks like Lego blocks. The world we live in today is full of saran wrapped toys that you can buy that you can't fix, fidget, or modify, but any type is really powerful in allowing the capabilities of the developer, the user, the regular Joe to be able to do a lot of advanced stuff. And that's why I kind of love it, and I've been following it for a long time. Congrats on your fundraise. Looking forward to see how you will grow the company and also the features, and give local first more love. All right, this is the part of the talk where we usually would have Q&A. If anybody wants to speak, the recording and broadcast